In this video, I go over a few multi-part problems involving multi-dimensional kinematics, i.e. motion in multiple directions. It includes a couple of Explore apps for educational purposes. For the newer users, I've decided not to include vector signs or subscripts. While both make the code more readable, they can sometimes lead to problems. Let's get started. We begin with a problem that involves a parameterized expression for position involving big R and big T, which claims to show circular motion. And this will be clearly in the X and Y directions, no T component. We are to sketch this out for some example values. We are to derive the expression for the velocity and acceleration, and we're supposed to describe how does the acceleration relate to position. So the first thing we do is to write out the R vector expression, which, as you note, I have not put the vector signs over. This will make it easier for you to reproduce what I do. And because there's no Z component, I'm going to ignore that term. Next, since we don't want R and T to change permanently, let's evaluate this at a particular R, T values that I just made up and create a new vector, which is not a function of T, just an expression, which we will be used to plot. From the plot of the X component, which is the first component, and the Y component, which is the second component, we can see how X goes to negative and then back to its original spot at 2 time units. Y starts at the origin, goes positive, then negative, and returns to the original spot at 2 time units. Not only can we plot the X and Y components, but we can parameterize them and plot them all on a XY grid. And as we can see, we do get a circular motion for which the radius appears to be somewhere between 1.1 and 1.5. While these two plots should tell us what the meaning of R and T are, big T meaning the total period and R meaning the radius of our circle, we can also animate this plot. We click on it, we push play, and our object travels in a circular motion for 3 time units. And it's fairly clear that if we go back in time, there is the point where it passes the 2 time unit. So here's our conclusion. By the way, in your textbook, they may define omega, the angular frequency, as 2 pi over the period. This way, you may see this parameterized expression as r times cosine of omega t instead of cosine of 2 pi over big T times t. That's what angular frequency is, a rewriting of 1 over period. Part B says, let's figure out the velocity and the acceleration expressions given our positional expression, which is a function of time. So that means we're going to take the derivative of our vector with respect to time. Notice we will get a result which is an expression, not a function. It has, again, an X component, the first one, and a Y component, the second one. If you try to turn this vector expression into a function of T, which is using make function, you will get an ugly output. It doesn't really matter. It is a vector. In fact, it's a column vector for which if you ask what is its value at some value T, that's what it looks like. Let's repeat the same for acceleration. Acceleration is the derivative of the velocity vector. I'll make a function out of it. So the next part says, how does our function for acceleration compared to our function for position? And you will notice there's a cosine term in the X component, a sine term in the Y component, just like that in position. In fact, if we compare the X component of the acceleration to the X component of position, the Y component of acceleration to the Y component of position, you'll notice that basically the two are the same except for this one factor minus 4 pi squared over T. So acceleration is always negative, opposite the direction of position, and it is always off by this 4 pi squared over T squared term. Writing that out as vectors, again, you can see acceleration is equal to the negative of this square term of R squared, R, or if you prefer the angular frequency component, it's minus omega squared times R. Our next problem is a projectile motion problem with no air resistance. Having no air resistance is a little silly, but it's not a bad approximation if the distance you're throwing the object or tossing it is short and the object itself is quite dense. It does not work for anything involving baseball. We are to derive the position of the projectile as a function of time. We are to plot the trajectory of the projectile, and we are to figure out how long it is in the air and how far it travels. We're going to assume it starts at the origin and ends up at the same height, y equals 0. Make your life a lot easier. Start at the origin. There's a vector showing position. The initial speed of the object is v sub 0, and the angle is some positive angle measured off the positive x-axis. The solution, or the physics, is the same as before. Use the definitions of velocity and acceleration. However, in this particular case, we know that the acceleration has no x component. The acceleration to the Earth is negative g, and there's no component in the z direction. So all our acceleration is straight down. We begin by writing out the differential equations for velocity and acceleration, and we note that the position and the velocity is a 3-component term, as is acceleration. Our system will start at some initial location with some initial velocity. Our initial location is the origin 0, 0, 0. And for our initial velocity, we note that the velocity vector in the 2 dimensions has an x component and a y component. Its magnitude is the launch speed, v0. The angle is measured off the positive x-axis. It's theta. Looking at the geometry, we can write out the expression for the x component and the y component. The x component is the magnitude times the cosine of the angle. That's this component. The y component is the angle times the sine, because the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. At this point, we have 2 rate equations and some initial equations. It's always useful to write out what we're actually going to be solving. If I hit enter here, you can see that we have 1, 2, 3, 4 vector equations with 3 components in each vector. And so now we're ready to solve this differential equation given our 2 definitions and the initial conditions. And if you see, you're going to get results that you might see in your textbook for the x component of velocity, the y component of velocity, the x position as a function of time, and the y position as a function of time. At this point, we can now extract out of our solutions the x component, the y component, make a vector out of them, and in fact actually then make a function out of them. Because at this point it's time to do part B, which says let's launch it with 2.4 meters per second of the speed at a launch angle of 60 degrees, which we have to convert to radians by multiplying by pi and dividing by 80. G is 9.8. This allows us to build a particular function to plot, but before we plot it, we have to figure out when does the object return back to a y position, the second, of 0. Notice I use Maple to say look between a very small value greater than 0 and 4, because we know it starts at 0. We can plot both the x component and the y component versus time. And we can make a parameterized plot of the x, y, as t goes from 0 to the final time. And since we already know what the time it takes for it to reach the bottom, we can ask how far does it travel, that is, when it reaches a time of t final. So the final solution is that the time it takes for it to travel in the air is 0.42 seconds, for which it travels a distance of 0.51 meters. As a bonus, I have made an explorer of the projectile plot, which does the process of calculating the time which the object reaches the ground and then plotting the position x and y as a parameterized plot versus time. You allow it to vary this initial speed and the launch angle. As you can see, the launch speed changes the distance that the object travels, as well as does the launch angle. Our last problem is rarely seen in introductory physics, and yet it should, because it's interesting. I want to shoot a basketball into the net. I know that I've put the least amount of effort into it. It will travel with the least amount of velocity. Therefore, it will have the softest bounce. Should I slightly undershoot or overshoot the ball? Is there a minimal launch speed and a appropriate angle to make this effort work? We're going to set up the same situation now, where we know that eventually the ball has to travel a distance L and up to a height h. Since I've already solved the projectile motion problem, assuming no air resistance, okay, we will use that expression for the x component and the y component, the z component, as a function of time. Literally, this is the equation we need to solve, that the x must reach a L, the y must reach a h, and we don't care about z. We solve this equation for the unknowns, in this case, the launch speed and the time which the ball is in the air, and we find that we get root solutions. So, extract out all the values of these root solutions, and we see we get two sets of solutions. This one involves positive time, the second one involves negative time. We'll use the first solution. Extracting out the first solution for V0, simplifying in, we know that L is greater than 0 and G is greater than 0, and trying for some particular values for distance and height above where I launch the ball, we get a plot of the velocity versus angle starting from 0, which is shooting straight horizontally, to straight up. And it's fairly clear that there is a minimum value for the launch speed, which will put the ball into the location of L equals 1.2, H equals 0.4. Time to solve for that minimal angle. That means take the derivative of our expression for velocity with respect to angle and set it equal to 0. That's the slope at that location. Solve for the angle, and we get two results. We'll choose the positive one, for which we'll make a function out of it with respect to L and H, and then of course calculate the V0 minimum function, which is a function now of L and H. Does our solution make sense from the classic projectile motion where it reaches the same altitude as it started? The answer is yes. You get the same launch velocity of the square root of g times L, and you get the same launch angle, which is pi over 4 radians or 45 degrees. And as a bonus, I made another explore of the plot. This projectile plot will consist of many components which we explore. The advantage here is that you can change the L, the distance it travels, and the height at which it has to reach the object, and you can see the launch angle. You can download the document associated with this video and play with the Explore app. If you do, you will notice the optimal angle bisects the angle of the line towards the basket and the vertical axis.